Good morning, everyone, and welcome to episode 272 of the Night Show, online index reorg for Db2 pureScale. I'm your host, Mohan Saraswatikara. I'm thrilled to have you join with us today. Before we dive deep into today's topic, I would like to thank all of you for joining us and then growing our Db2 community. Your passion for Db2 and continuous learning is what keeps this show thriving episode after episode. In every session, our goal is to share actionable insights you can take back to your own environment, highlights new features, capabilities, showcase practical tuning, administration, and performance tuning insights. And we will begin with a brief introduction and then a quick polling session to understand our audience environment. Right? Thanks again for joining. And we have the special guest today, Wei from IBM Toronto Lab. Hi, Wei, how are you doing?
Hi, Mohan. I'm doing great. Thank you. How are you doing?
Yeah, doing very well. Thanks for joining us. Thanks for taking time.
Yep.
Awesome. Get involved. So please do follow us on Twitter, X, and all our replays are available within the DB2Night Show website and also on YouTube. The YouTube channel, Db2Night Show 770. Please follow us, subscribe us, and also join us on LinkedIn. We will have a lot of postings with information about the sessions will be posted on LinkedIn. Disclaimer. All right. Tonight's show, we have online index reorg for pureScale. We have a lot of sessions from lab this year, starting, we had a full Db2 12.1 session from Mike, and then Michael took the logs, internals of transaction log, and ASML. All that was completed. Now Wei is going to take you through the pureScale reorg feature and the future. We have a security presentation coming. Michael coming back again to talk about the recovery problems, everyday problems and solution, and AI optimizer. Bring your own cloud. That's for Azure, and AI vectors for AI. And then the last one is going to be digital. That's going to be intelligent center for Db2. We have a lot of sessions coming this year. Be prepared to join as and when the link is posted. Thanks for our sponsor, DBI, Smarter Tools for Smarter People. DBI tools are supporting both DB2 as well as SQL Server. This is one-stop shop for your performance fine-tuning and performance tuning aspects of SQL statements. Right? We were going to be having a few polling questions. It's going to come on your screen, and we'll have 30 seconds for each of those. All right. Collecting the responses. All right, collecting the responses, closing the poll in 5 seconds. Right. Closing the poll, sharing the result. Looks like pretty nice. 12.1 and then 11.58, 11.9. That's great. Are you using automatic maintenance in production? Collecting the responses. Closing the poll, sharing the result. 100%. Everybody said they are using automatic maintenance. That's good to know. Are you running Db2 pureScale? Okay, collecting responses. Closing the poll, sharing the results. 75% said yes and 25% no. That's good. Well, that's a lot of participants are from pureScale area. All right, what are your environment challenges? Collecting the responses. Okay. Closing the poll, sharing the results. A lot. Yeah, so performance is about 25%. That's interesting. It used to take most of the results, most of the performance problems, but now this is about 25%, and data growth is 25%, and resilience is about 50%. Cool. Okay, one other question. Are you running HADR with pacemaker in production? Okay, collecting the responses. Closing the poll, sharing the results. About 20% yes, 60% they're still on DSA, and 20% no, it's a standalone database. Okay. Right. Again, we're back now to Db2Night Show episode 272, Online Index Reorg for pureScale. We are excited to welcome Wei, Senior Product Manager for IBM Data and AI, who will walk us through online index reorg for Db2 pureScale, an essential topic for maintaining high performance and availability in enterprise environments. Stay tuned for the best practices, performance tuning tips, and real-world use cases. I'm gonna make you as a presenter.
Yep, thank you.
Okay, you should be getting a pop-up on the screen.
Yep. Can you see my screen?
Not yet. Just waiting.
Okay.
Please do post the question in the chat. You will have a chat session open below in the webinar section. You can post the questions as and when you have it in mind. We can then route it to be. I can see your screen now.
Awesome. Okay.
Great.
So, yep.
Thanks,
Thank you
Wei.
for having me. Yeah. Let's get started. So today's topic, online index reorg for pureScale. Okay. Let's move on to the next one. Disclaimer. So this is a standard safe harbor statement. Anything forward-looking is subject to change. All right. Okay, so agenda for today. Before we dive into the new feature, online index reorg rebuild for pureScale, I will first cover some key fundamental foundations for index. First is a quick refresher on index in fundamentals, how they are structured, and why they could degrade over time. Then I will walk through some reorg strategies, cleanup versus reclaim extents, online versus offline, and how to keep indexes healthy and efficient. So last, we'll look into the new feature online rebuild capability in PureScale, how it works and how to monitor it. Okay, so first, a refresher on index fundamentals in DB2. So an index is a physical database object that stores assorted key values from one or more columns with the pointers to the actual data. So the data could be a row in the base table or a block in the MDC, ITC table, or even XML data, okay? And logically, indexes are organized as B class trees with root, intermediate, and the leaf nodes to enable fast and efficient searches, okay? So in DB2, the tree, the indexes serve for three major purposes. So one is to speed up data access. The second is to get data integrity enforced, like a primary key or uniqueness. And the third is to help with those sorted operations. Then the considerations, so indexes are not coming free. They slow down writes. If there are lots of IUDs, the indexes need to be maintained, right? They also consume storage. And then if there are too many indexes, it will increase query compilation time. So that's why index design should be very thoughtful on choosing the right columns, using the compression to save space, and also keep the indexes healthy through the regular run stats or reorg. All right, so this is a refresher for the fundamentals. Next is a quick review of typical types of indexes. So first, the unique index, of course, enforce a uniqueness. And the next is clustering indexes. These align the physical rows with the index order. It's great for performance for range scans and ordered queries. Keep in mind, there's only one clustering index allowed per table. All right, so for range partitioned tables, we have partitioned versus non-partitioned indexes. So partitioned indexes offer partition level maintenance, but non-partitioned indexes, we also call it global indexes, it spans the entire table. All right. Then XML indexes speed up XML queries, and the block indexes, which used by MDC and ITC tables, they cluster data based on dimensions. Next, we have expression-based indexes, which pre-compute expressions for faster filtering, and random indexes, which is particular for reduced contention in PureScale. And then we have modification state indexes, which for CDE table, column organize the tables to track visibility of changes under CS semantics, which is currently committed semantics, okay? And the last is the page map index, which is an internal index that you will hear a lot when you're dealing with column organized table. It tracks page allocation for CDE tables. Okay, so this is a quick review of type of indexes. Next, we'll have a closer look at how indexes are structured inside the DB2, specific and the index page level and the index object level. So understanding this page level and object level structure will help you make a better, wiser decision around the reorg, partitioning, and the storage layout for a large system. So in DB2, indexes are made up of pages on disk, okay? All the pages of a table's indexes are logically grouped into an index object. So on the left is an index in page level. So each index page has a header followed by a slot directory. Each directory pointing to a read or pointing to a block. Then for leaf page, it contains the keys and pointers. And for non-leaf page, it has pointers to the child page in the next level in the B+ tree. Okay. On the right, that's a diagram show the index object. So for non-partitioned tables, there's only one index object for contain all the indexes defined on the table. But for partitioned tables, we'll have one index object per partition for local indexes and one per global indexes, which is also called non-partitioned indexes. All right, so for each index object, you will say there is a meta index, which is by itself is also a B+ tree. It tracks all the defined indexes within this object using the index unique ID and the root page. Okay, and in this diagram, you will also say there's a SMP page that tracks the index page allocation within the index object. When the index object is big, there could be multiple SMP pages. They are chained together. All right, so this is the per page level and the per object level structure review. This layered structure will support the faster access and the flexible storage. Okay, next, this is a review of read index and the bit index. So on the left, you will see a read index which is used in the traditional tables. Each index record has the record ID, which points to the data page. For example, here, 4023 and the slot 2, it points to the data page 4023 and the slot 2. And on the right, you see a block index, which is used for the MDC or ITC table. Instead of pointing to a row in the table, it pointing to the block. So it used the block ID to map back to the group of pages with rows. All right. I'm gonna move on to the next, which is index tree search. So let's have a quick look at how DB2 search is using a B+ tree. On the screen, you see the 3-level index tree: root node, intermediate node, and the leaf node. So we start the search at the root. So let's say we want to say everything greater or equal than P. So down through the roots, we get to the leaf, get to the intermediate page. From there, there's a child pointer. We go to the leaf page. The leaf points us to the actual data page with the matching rows. So this red path shows a range scan starting at P. This tree structure will keep the search faster even on the huge tables. Keep in mind, when table is huge, the index size is much smaller than the table size. Okay, so next is the index tree modifications. So we revisit the tree search. So next for the updates of the tree. When there's a row inserted to the base table, the key is ended afterward. And when there's the row is deleted, the key will be marked pseudo deleted. During the update of the row, DB2 will delete the old key and then insert to the new one if the update affects the index key columns. Okay, so what's a pseudo deleted key? Those are index entries marked as deleted but not removed immediately if the table is not locked exclusively. All right, and those pseudo deleted keys can be reused for identical inserts later by DB2, or they can be cleaned up after commit, either by next modification transaction or by a reorg indexes cleanup. Okay. Then when the tree is getting updated, index leaf could be split or be merged. So the tree structure will be modified. So we call those tree structure modification operations, in short SMOs. Those tree modification operations will be synchronized with a concurrent access to the tree to ensure everyone have a consistent view of the tree. All right. So on this part, there's a type 1 index and type 2 index comparison. So this will show us why we use pseudo deleted keys. So with the type 1, we'll have this false lock conflicts if we are not locking, if we are not inserting the relevant key. And if when we move on to the type 2, we use the pseudo deletes, which avoids the false conflicts and provides a better concurrency. Okay, so this is a review of the tree modification and pseudo delete keys, and also why we choose pseudo delete keys in DB2. All right, so we reviewed how DB2 perform tree search and modifications when the table grows or shrink or go through those frequent insert delete updates. Those change will gradually affect the structure of the tree. So that could lead to index degradation over time. On the performance side, the degraded indexes often suffer from the fragmented leaf pages, where more leaf pages records are needed to fetch to get the table rows. And also, we could say low density pages where sequential prefetching becomes inefficient. And when the tree getting deeper, it will lead to higher scan cost and locking contentions. Okay, so for the space perspective, it means index could get bigger and bloating, and the pages are left half full, and pseudo deleted pages linger, and the disk get consumed by those zombie entries, which has little use for the queries. All right, so this is index degradation impact for performance and for the space. Then what we do when indexes start to degrade? The next section I'm gonna talk about is strategies about index reorg, which help us to reclaim space and improve performance and avoid costly full rebuild. Okay, so let's take a look. There are 4 major ways to reorg an index in DB2. Rebuild is the most aggressive one. It recreates the whole index, reorders the leaf page, and reduces the tree levels. It's best to use this one when the index is really heavily fragmented. The cleanup comes in 2 flavors. All and the pages. So it clears out pseudo deleted entries and empty pages. It makes the index more compact, but it doesn't change the tree levels. Okay, it cannot shrink the tree. Reclaim extends. It moves pages around to free up space and return unused extents to the table space. So it's great when other tables in the same table space need the space. Okay, so each of them has its own role, and whether it's performance or space or cleanup, we'll dive into the use case of each of them in the later slides. So here, this slide is a reorg options in terms of the availability and the space usage. Okay, so rebuild, allow no access, is the most disruptive one. It rebuilds the index in place and block access until it's done. Okay, so this index object in gray means there's no access, and the rebuild is happening in place. You don't need additional table space. Okay, the shadow-based rebuild approach improve the access. They create a new copy first, okay, and then swap it in. So allow write can allow the concurrent writer transactions, but it needs a log replay to reflect the change to the shadow index object. So both allow read and allow write, they need extra space, and they have a very brief no access window when we switch the shadow with the real object. Okay, the last one is in-place compaction. This is the least disruptive one. It does not rebuild the index. It deletes or clear out pseudo delete keys and merges leaf pages while keeping the index online. Okay, so depending on your availability needs and the space situation, you can choose between the full rebuild or the lighter touch cleanup option. Okay, so next is specific for reorg cleanup versus reclaim extents. They both help with the space, but in different ways. So cleanup removes old keys and empty pages, making space reusable within the same index. Okay, reclaim extents goes further. It reorganizes pages to free up full extents and return them to the table space. So for best results, you can run cleanup first, then reclaim, or you can combine both in one run. Both of them allow read and write access. So depending on how you run up. And keep in mind the reclaim extents end to the end before releasing the free space, it has to wait for the concurrent transaction to complete. All right, so the takeaway for this is use cleanup for local compaction and for reclaim extents to give the space back to table space so other tables can use it. All right, so next one is a comparison between the offline and online reorg rebuild. Online rebuild creates a shadow index in the same table space. With read access, query can still run, but no updates. And with the write access, both read and writes continue, and the changes are replayed to the shadow, as mentioned before. And at the end, the shadow swaps in and the original one is dropped. Okay, so it gives a minimum downtime. Offline rebuild is done in place. There's no access to the table during the operation, not even read. It's simpler and usually faster, but requires full isolation. Okay, so if you need to keep access going, go with online, and if you can afford downtime in maintenance window, offline is the most direct one. All right, so since the rebuild is the most aggressive and the disruptive index reorg, it should be the last result, and there are ways to avoid it. So read ahead prefetching. It's a better, in recent versions, it doesn't need to reorder pages to get some performance boost, okay? The next is you can try % free or level 2% free when creating an index. This will help to reduce page split. And you can use the mean % used to let DB2 to defragment the indexes online. So page merge, which happening for leaf page, will happen during the online runtime operations. Okay, and then try the cleanup and the reclaim extents. They are lightweight and work well for most cases. So since 11.5.9, Auto Reorg also supports the cleanup reclaim extents for MDC, ITC, and partitioned tables, making use of max offline reorg table size parameter. Okay, so with the right settings and the cleanup strategy, you can, most of the time, you don't need to do a full reorg rebuild. All right. So this slide will show an example for a best practice to reclaim index space online with reorg indexes, cleanup all, and the reclaim extents. So we have an index on invoice data. After a batch delete, many pages are left sparse with pseudo deleted keys. Now, we can do a cleanup all, remove those keys and merge pages, but keep in mind the space has not been returned yet. So next you can try reclaim extents, which will reorganize the pages to group pages together to form the empty extents and then return those empty extents back to table space. Okay, so the tip here is to run both operations or both options in one reorg command together for best results. It's faster and it's online. All right, so the next is a query to show you to know when to run reorg cleanup or reclaim extents. This can be achieved by check the reclaim space from the admin get index info. Okay, once you see the indicator here, then you can try the index reorg cleanup all and the reclaim extents to get the space returned back to table space. All right, so more tips for reorg rebuild. If you cannot avoid a full rebuild, what other strategies or options is, one of them is divide conquer by the data partitioning. If you are using local indexes, you can run online index reorg per partition to reduce the log and the space requirements, and you can run concurrent reorgs on different partitions. Okay, for global or non-partitioned indexes, you can reorg each index individually online. Remember, we mentioned like global index resides in its own index object. Now, there's a tip to get per index reorg. So you can create a table with only one data partition, make it a range partition table, and then create indexes as global ones. Then you can achieve reorg each index individually. All right. Okay, so with even a large table, high volume system, smart use of partitioning can make your index reorg faster and lighter and easier to manage. Okay. Next section will explore the best practice for index reorg and also the new feature for the pureScale environment online index reorg rebuild. Before I move on to the next section, any questions?
No, I don't have any questions here in the chat. Thank you.
Okay, Mohan, are you saying there's no questions?
No questions here, but I have one in general. Let's say I have 10 indexes on the table. When I perform table level reorg, are we going to commit at the end of all 10 indexes, or are we committing at every index reorg completion time?
That's a great question. So for table reorg, we typically have online and offline, right? So classic table reorg, and to the end, the index object, the whole index object will be rebuilt. And that time, there's no access to the base table, right? So that one shot, you do a classical table reorg, and the index will be rebuilt. Then we have the online table reorg. For online table reorg, the index will be maintained online. There's no rebuild at the end. So anytime when there's concurrent access to the table, do modification, the index will be maintained online.
Got it.
Okay. All right. If no more questions, I'll move on to the next section.
Sure. Thank you.
Okay, great. So then this section is all about the new feature for pureScale. First of all, I wanted to quickly revisit what Db2 pureScale is all about, right? It's designed for high availability and the scalability in OLTP workloads with shared everything architecture for all members, say the same data, and the clients can connect it to any member, okay? And the multiple Db2 engines run on the separate hosts coordinated by the CS, which is cluster services, and high-speed interconnect. The CF, which is a cluster caching facility, ensures global locking and the buffer consistency. And each member, keep in mind, writes its own logs, but recovery can happen from any node. And in short, pureScale delivers continuous availability and seamless scaling and consistent performance. So that's why index performance is so critical in pureScale. And the day two operations like a reorg index must keep the system online and the responsiveness, okay? So this is overview of pureScale overall architecture. Now let's have a quick review to see what we have for index reorg in pureScale. In early Db2 versions before 12.1.1, reorg rebuild in pureScale only work with allow no access. That means no read, no writes. All right. And the cleanup pages and the reclaim extents, those have always supported online, even with allow write for pureScale. Okay. And then what's new in 12.1.1? We starting from 12.1.1, reorg rebuild can now run online. You can use allow read and allow write, and you can get the benefits of a full rebuild without taking the application offline. So you will not get this restriction anymore. All right. Next, we'll deep dive on the allow read access from a timeline perspective. So this process starts with reorg index allow no access, allow read access command, which can be initiated from any member. Like mentioned before, clients can connect in pureScale in any member. So we begin in a read-only phase where reader across member continue unaffected, right? But writers are blocked. The table or partition is locked in the ulog, then a shadow index object is created, okay? Then we sequentially to build each index in the shadow object. All right, all the read access remains when we build the shadow object, okay? Next, we'll have a very brief no access phase So starting from here, there's no access because we lock table or partition in Zlog. And we'll prepare the shadow index for switch and the write pending list action, okay? And then we proceed to the commit time. And this time we'll switch the shadow object with a real object, invalidate the reference to the old index, and then drop the original or real index. All right, and last, when transaction finished, we release the Zlog. After that, the full read-write access will resume. Okay, so this is a timeline for index reorg rebuild, allow read access in pureScale.
This happens at the start of the no access mode in 23 slide number. Do we know how long this is going to take from the time you take the exclusive lock, the super exclusive lock Z, and you come in? Is that based on the amount of data we have in the index, or just about the swapping time of the index, dropping and renaming this?
Yeah, that's awesome. Ask a question. So answer end. So when we switch shadow index object, we need to flash, right? So flash depending on the size of the object. It usually will be really quick.
Okay. And does it, for example, if I have a read request coming into my table, started my reorg with rebuild, allow read access. Since I'm continuously reading that table and that specific index, is that going to get you a lock weight here with the killing this reorg session with 91168?
Right. So if your read is a UR doesn't take lock at all, so it will be blocked. It will not be blocked.
Block it? Intent non-lock?
Yeah.
Okay.
Yeah, but because you don't take lock, but if your scan or read is like a CES or RR or IS scan, it takes locks, right? So at the end, when we do the switch, we block everybody. So you won't be able to proceed. You have to wait, right? Once we finish, then you can proceed. But if you have this lock timeout, and if you reach lock timeout, you probably will get 901.
Right.
Okay. Yeah, you're welcome. All right, so next, let's move on to the allow write access. This slide has more stuff here. So this is the index reorg rebuild, allow write access timeline in pureScale. So same as before, the reorg command can be initiated from any member. And it begins by lock the table or partition in IN mode, so different than before. The before is U mode, so nobody can do writes, right? But you lock it in IN mode, you allow writes. Then next will block online and member, which for pureScale we don't support it for online, to support online and member for this feature. And then same as allow read access. For allow write access, we also use a shadow copy. So we need to create a shadow index object. Okay. Then the new stuff for this one is we need to allocate a shared memory in CF. Okay. That's the information to coordinate all the members. So everyone need to go to CF to consult what's happening in the cluster. So we need that shared memory in CF. Okay. Then next stage, we start to build each index sequentially in the shadow object. So before we start each index build, concurrent writers continue to update the base table, but we have to draw a line to get concurrent writer to aware there's a reorg. So those concurrent writers has to be drained, right? So the existing one will be drained and the new writers will be allowed. Okay, and then those writers, all the concurrent writers will do additional logging for the catch-up phase. Okay. Then the shadow index is is built and brought up to date by applying changes from a concurrent transaction. If the catch-up is kind of slow, the reorg will move on to the next index. It will not wait on this index forever. We are smarter, we move on to the next one. And then for the final catch-up, which means the last index to be rebuilt in this reorg, ulock is acquired to complete the final catch-up, which means nobody can do the write, but you can still do the read, right? So it will help the reorg to complete the catch-up and complete the operation and move on to the next stage. Okay, so the next stage, there will be a brief no access phase, similar like allow read, which we lock table or partition in zlock, exclusive lock. And then we prepare shadow index object for switch, and we write the pending list action. Okay, and then move on to the commit time. The switch will happen for the shadow and the real object, and the same as allow read will invalidate references to the old indexes. And the difference between the read and write is here. We allocated the shared memory. Now we need to do the cleanup of the shared memory. So the number 4 step is to drop the original index, and at the end of the transaction, we release the zlock. Okay, after this point of time, all the full access will be resumed, like read and write will be resumed. Okay. Next, this is the architecture view of allow read access. So previous 2 slides is the flow per timeline. So this one is per cluster architecture view for the allow write access of the index reorg rebuild. Same as before, the reorg can start on any member. So here on the screen, we say reorg start from member X. Okay, and we have IUD member 0, IUD member 1, and etc. If you have 10, you can have any IUD from any member when the online reorg is happening. Okay. And one thing to keep in mind, only one rebuild can occur on the table at one time, but multiple reorgs can run in parallel across different tables, okay, on different members in different access mode. All right. IUDs, like mentioned, can happen on all members. The reorg will start with an initialization phase. So like mentioned before, an IN table lock or partition lock is acquired, and the shadow index object is created, and the shared memory is allocated in CF to coordinate between members. And then reorg waits for all active writers to join, and then writes the special log markers to track the point from which changes must be applied to the new indexes. Okay, then move on to the next phase. That's the build for the index for each index. Okay, in the build phase, we scan the table and the build index from bottom up into the shadow object. Okay. Then comes to the log catch-up phase, which is central to allowing concurrent writers. As the new transaction continue to happen, all the members write special log records, and the older member, so this member will initiate a log reads from all the log streams. Okay, then read the log into the local buffer, and the log catch-up will know where to start to replay and apply each of them to the shadow index, which will ensure consistency between the table and the newly reorged rebuild index. Okay, the catch up is done after each index is built. Okay, we'll catch up to the current end of the log. If the new log record, say if you have a heavy workload and the new log records will keep coming and too fast, and the owner cannot, the online index reorg cannot catch up in time, then the reorg will move on to the next index to keep the reorg progressing. Okay, then for the final index, we'll upgrade the table log to U mode and stop new IUD activities. Starting from this point on, nobody can do writes. Nobody can write additional special log records. Okay, so this will allow us to catch up 100% of the remaining log records and then able to move on to the completion and the cleanup phase. Okay, so in the completion and the cleanup phase, we upgrade to Zlog, switch the shadow with the real, and make sure nobody will access the old indexes anymore, and then freeze the shared memory, and then drop the original index. So in this point of time, sure, we do have a brief no access window, like Mohan asked before. Depending on the size of the index object, the time could be different, but in general, it should be quick. Okay, so this is architecture view of the allow write access. All right, so this slide is a recap, in the text format to recap the rebuild phase, which has been covered earlier. So I will not cover each of them, and I will move on to the next slide. So the locking and the concurrency control. We mentioned about the table lock. So these slides will also have the information show the type of the locks in the higher level acquired during the index rebuild or index cleanup or reclaim extents. So as the higher hierarchy of locking perspective, reorg rebuild always acquire an IX lock on the table space to ensure table space stay intact. And we also have an X alter table lock to prevent multiple reorg and creates happening at the same time. And we also have the table locks on the sys tables or sys data partitions, and also the row lock. Make sure nobody can touch those records in the catalog. Okay, then like mentioned before, for allow read, for allow write, we have the U lock for final catch up, so nobody can write anymore. And for allow read write, a Z lock taken briefly during the switch phase. So if the rebuild is on a specific partition, the partition is also locked alongside the table lock. Okay, so this is for the locking perspective. Then next, runtime rollback. So there has to be some situations, there's an interrupt or there's a control C, or in rare cases, if there's a failure happened during index rebuild, what's gonna happen, right? So that's gonna trigger runtime rollback. So reorg operations will be fully rolled back. The system will safely undo the rebuild process in the background, and the original indexes will remain untouched. So ongoing queries continue to operate without disruption, okay? However, there is a brief moment where writer activity is paused, just long enough to clean up the shadow index and release resources, Okay, so you can monitor the rollback progress, use get snapshot for all applications. And on the screen, there's an example, right? So for the rollback activity, that's a transaction rollback. Completed work shows how many bytes, log record to has completed, and the total work, it's overall how much work to do, okay? So this is for rollback, and the next is recovery, okay? In the extreme cases or in the restore, roll forward, and HADR, we needed to have those understanding about this reorg, how we're gonna to perform the recovery, right? So the first is when there's no writers involved for recovery scenario, which includes the group crash recovery, which is in pureScale, and the roll forward, and also HADR standby replay. So behavior is same as non-pureScale, just a standard redo undo transactions, which has the reorg operation. Okay, then for the scenario where writers are present, for example, member crash recovery, some recovery tasks may be delayed until after crash recovery to avoid circular dependency. So we want to avoid those deadlocks, right? So we have to do something special here. So the system must return logs and spawn a thread and complete the cleanup automatically. No user intervention is needed. This is all self-managed by recovery logic. And this work is not needed. It's not always needed in the members crash recovery. It's only needed when the table lock is not held in U or Z at the time of crash. So when the table lock is held in exclusive mode or in the U mode, then we don't need to do this special handling because there's no risk of circular dependency, okay? So how to monitor it? So Db2 PD dash recovery. It will give you information about where we are for the recovery, okay? Next, so limitations for this feature and restrictions. First of all, circular logging is not supported. And then second is online and member, like mentioned, is not allowed during index reorg with write access. If a member is in the process of being ended, that pending state will block index reorg, okay? Then the next is extend movement and the table space reclaim operations. Those are paused for the duration of the rebuild to avoid conflicts, okay? Then the number of index per table. So there is a limit, 200 per table or per partition. That should be sufficient for most use cases. Like mentioned before, too many indexes hurts, right? 200, that's a lot, right? And finally, the rebuild cannot run while the cluster is at a mixed level. So this is a pureScale. So such as rolling updates, this feature cannot be run if you're doing rolling updates. This ensures the stability across all members, all right? Performance tuning. So this is a fun chart or slides, a lot of aspects you can consider. So first, for you have to make sure the actual log space is healthy to support the long running reorg, okay, if your table index is big, okay. Next, make sure your index table space has enough free space and can grow quickly. So turning on fast pre-allocation may be able to help here, okay? The next is consider placing the index in a separate table space to reduce contention with the base table. Like mentioned before, index for allow read and allow write, they build a shadow in the same table space, okay? Then you can try run the reorg during the low write activity periods, okay? This will minimize the amount of log catch-up needed and shorten the final catch-up phase, okay? Page cleaners. So like mentioned before, in the switching of a shadow, we do flush, right? In pureScale, flush from local buffer pool or GBP to disk. So make sure the page cleaner are doing their job efficiently so that dirty page don't delay final cleanup when writers are briefly blocked. Okay, on the right side, there are some memory tuning. So index build needs sort, right? Sort heap, that will, you may need to consider increase it, and the sort heap threshold, that's also control, that control cluster wide, like instance wide cap for sort memory. So make sure you have a good ratio of a sort heap threshold to sort heap, and this will help avoid the sort overflow. And lastly, utility heap size. So set it to a large enough to support update heavy workload. If you have lots of IUDs, we need the buffers, right? Those are from the utility heap. So make sure that has a reasonable good size. So that's all the tips I can think of. And this will, adjusting those will help keep reorg efficient and reduce the unexpected stalls. All right. So next is a tool, reorg check. So how do you know index need to reorg? This is a tool to assess the need. Okay, but keep in mind, this is recommend. It's not mandatory. Okay, so this slide shows F4 to F8, different formula, what's the purpose. I will not read through each of them. So info is here for your reference. And here is an example. So you do reorg check update statistics on one table, and this will show you the results of each formula. And in this example, F5, F6 are good for index 1, but F8 is no good. So reorg is recommended. And for index 2, F6 and F8 both fails. So reorg is strongly recommended. Okay, so this is a tool, is very helpful. You can use that to determine or recommend you when to do the index reorg. Of course, this one also can use for the table reorg as well. So monitoring, if you have a reorg, index reorg is ongoing or has done some index reorg in the past, how you monitor that. So Db2 PD -reorgs index, this option will give you that information. And also you can use list history reorg, or for example, in the example, my DB code sample, okay? So this will give you the history info as well, okay? One thing to keep in mind for pureScale, so the Db2 PD only shows the reorg on the member where the reorg is issued in the cluster. If you want to query all the reorg issued across the cluster, you have to use db2_all, okay? All right. I think, yeah, that's a presentation. Okay, then takeaway. So make sure you minimize the need for full reorg rebuild, because that's a heavy operation, like mentioned before, fully rebuild. And then choose the right one. Sometimes you don't really need to rebuild. You only need to clean up or reclaim extents, right? And how you monitor, use those tools as reference. Keep in mind, that's not mandatory. Make sure you do that in purpose, not by routine, right? Yeah, that's all for this night show.
Thanks, Wei. That's great. Yeah, a lot of insights. Thank you very much.
Thank you.
Yeah, big thanks to you today for sharing valuable insights and expert knowledge on reorg in general, and then online index reorg in pureScale in specific. Your contribution today for this session is truly enlightening, and then we're sure the audience found that to be very informative and practical as well. Thanks, Wei, again. I'm going to take the screen back. Okay, show my screen.
The broadcast is now starting. All attendees are in listen-only mode.
Not sure why it rebroadcasted again. Okay, that's interesting. We can hear me?
Yes.
Okay, that's interesting. It broadcasted again. Okay, cool. Today's show sponsor, DBI Software, trusted partner for performance tuning for SQL Server and DB2. This is one of the screenshots from the DBI product. It's a web-based product which helps you understanding what's happening in your database and fine-tune the queries and understand what the transaction throughput is and transaction write rates are and all that. With that, we're going to close today's session. Thanks again for your time and participation. We hope you all take useful knowledge of the session we had today, and we'll connect back again in the next episode.
Thank you, Mohan.
Everybody, have a good day.
Yeah, thank you. Have a good day.
Bye-bye.
Bye.